Ladies and gentlemen, we're going to start our exploration of chapter 10, which is alcohols. And before we study alcohols, we got a reminder about some reactions we've seen before. We saw this reaction before. In chapter 6, we saw if you took an alkene and reacted water with it, you could add water to the molecule, and you would get the new OH here, and there's a new H here that wasn't there before. And we call that hydration, acid-catalyzed hydration in chapter 6, using either toluene sulfonic acid or sulfuric acid gives the same result. This would be the major product. Flip these two for the minor product. Sometimes I don't ask about the minor product. And it should make sense that that's hydration is the opposite of dehydration. Very good. So get that activity back there. And we're off to the races here. We're going to learn the dehydration mechanism. It's a pretty straightforward one. There's two options. You're creating a pi bond, but you don't have a leaving group yet. So do you remember what happens when we create a pi bond and we had a leaving group to start with? We call that a specific kind of reaction. Reaction that makes a new pi bond. And do you remember what that was called in general? Grab a beta hydrogen, make a new pi bond between alpha and beta, and the leaving group leaves from alpha. Does this sound familiar? Because in chapter 9, we did exactly that. It was called elimination. Elimination makes pi bond. And yes, you're making a new pi bond. So question 1, why is dehydration endothermic? There's heat required, while hydration is exothermic. That's going backwards. It's exothermic. And you got to talk to me about stability when you talk about thermicity. Endothermic means you got to put heat in because the products are less stable than the reactants. So here's the translation of your question. Why is this product much less stable than the reactant? I will accept a one-letter answer if you use the right language. We don't use too many languages in this class. Why is this an endothermic process? Was translated to why is this product less stable than the reactant? You need only look at the pictures on the screen to tell me why this is less stable than this. That's not really anything to do with water, which is also a very stable molecule. It has to do with the nature of the bonding in this molecule compared to the nature of the bonding in this molecule. Compare the weakest bond in each one and determine that the weakest bond in this molecule is fundamentally weaker than the weakest bond in this molecule. Why? Okay, people watching the video are thinking too. What is it about this species that is less stable than this species? He said hyperconjugation? There is hyperconjugation that helps stabilize the unstable pi bond in here. And I have maybe inadvertently let out the answer to my question. One way I asked the question was, I will accept a one-letter answer as long as you use the right language. And I let out that letter slip in my words just a minute ago. That is not a letter of any alphabet. So, no. Okay. Clearly, I got a coffee break. We will do a pause And all right, we have an answer. This has a pi bond. This is all sigma. Pi, less stable than sigma. End of story. Endothermic reactions create products that are less stable than the reactants. Okay, so reactions of alcohols are not the same as the reactions in chapter 9. In chapter 9, we had a carbon attached to a leaving group. And then we could do SN1, SN2, E1, E2, NGP. We don't have a leaving group here. Do you know how I know that? That'd be question number 3. Why is an alcohol not a good leaving group? 3. Why is an OH minus not a good leaving group? We'll tackle that one next. Saving number 2 for later. Br minus is an excellent leaving group. Cl minus is an excellent leaving group. Hydrogen sulfate's an excellent leaving group. Nitrate's a good excellent leaving group. She's got an answer for me. They are the conjugate base of a strong acid, which means H is attached to an excellent leaving group. It's just another way to say it. Okay? Now, OH minus is the conjugate base of which acid? I'm writing this down. OH minus is the conjugate base of water. H2O. pKa equals what for water? 16. Because the pKa is 16, OH minus is unstable. Yeah. Okay, it's not a good leaving group. So conjugate base of strong acids, like she said, are the excellent leaving groups. So a theme in chapter 10 is before you can do a reaction of an alcohol, you've got to make it a better leaving group. That is a fundamental theme for making alcohols react. And we have the means here with the other chemical present to make the alcohol into a better leaving group. And it's a reaction we studied already. Why am I putting the lone pair on the O there? Take a wild guess. I'm going to do something with it. Yes, good answer. What am I going to do with it? Grab the hydrogen from our strong acid. Excellent. I can use either one. I was given this or that. We'll just go with hots. It was handy. We've got our oxonium that we just made. Water is a good leaving group. Is there a short form for leaving group I can use? Yes, Lg. Conj base of H3O plus, which is pKa negative 2, right? Or 3, you pick. And what do good leaving groups tend to do? It's in their name. They tend to leave. So if the mechanism has a secondary or a tertiary oxonium, in this case it's a secondary oxonium. If it's secondary or tertiary, this mechanism that you're about to do right now is the one you should do. Secondary or tertiary. You'll see primary in our example below, but we're not doing that example now. So what am I going to generate by doing that? This is E1, by the way. Starts here. If it's got a 1 at the end, what's the word in your mind for your intermediate? Either SN1 or E1. What's the word in your mind for your necessary intermediate? Thank you. Carbocation. soon as you hear SN1 or E1, you better think carbocation. So that's what I made by making that thing leave. A beautiful tertiary carbocation. And there's a reason why I'm putting this H over here, because we need it to become those things. Water's already left. What's going to grab that H? And you made it in the first step. Yes, plus OTS with a lone pair and a minus. The base. This is an acid catalyzed mechanism, isn't it? What do you think happens to the sigma bond there between the carbon and the blue H? It's going to the product. It becomes a pi bond between the methyl carbon and the adjacent carbon, right there. There you go. And that's an E1 mechanism. In chapter 9, E1 was never the whole deal. Chapter 10 and 9 are not the same. When you generate a leaving group this way, you're in a different environment than chapter 9 with all the acid around. It's a protic environment. Cation is favored. There we go. So what do we do in the next one? We start the same. What kind of alcohol is this one on the bottom of the screen? Primary. So our first example was a tertiary alcohol. Our next one is a primary alcohol. They both start the same. And you're going to remind me what was the purpose of this step? Why did I have to do this step? What was the purpose of protonating the O here? Well, what's it doing here? Leaving. It can't leave until it's protonated. Why? Answers on the screen. It can't leave as hydroxide because it's a poor leaving group. Why is an OH minus not a good leaving group? Okay. It can leave as an oxonium, which we're about to draw, because that is a good leaving group. Now, if you did the same mechanism as the previous one, you'd be in trouble because you'd be making a primary carbocation, which is haram. And that is not the first time this has been said. It has been said multiple times. So you do not have E1 as an option when your cation would be primary. What's the other E again? E2, in which case you never have a cation and you go straight to the product, which means you've got to show your base, of course, and this beta H. Oops, that's not the beta H. That's not there at all. It's here. Alpha's where the leaving group, beta's one away. Please remember to grab the H from the beta position. Things don't work if you grab an H from the alpha position. You can't get where you need to go. So that's an E2 right there. That one step is an E2. We got E1 slow, E1 fast upstairs. And that's only because you had a secondary Rx. Here you've got a primary Rx. And yes, if you've made it into a good leaving group, you can go ahead and call it Rx. Right? Chapter 9. What was X? Leaving group. Don't say that's an Rx when it's an alcohol, because it's not a leaving group. Okay. So what's our take-home message on dehydration? If you have a secondary alcohol or a tertiary alcohol, which mechanism, E1 or E2, sorry, E1 or E2. E1 for secondary or tertiary. If it makes a nice cation, you better make the cation. If you can't make a nice cation, you have to do the alternative, which is the 2, E2. And you got to make the leaving group so you can do the E2. So far, so good. And we never answered question 2. What is the difference between dehydration and condensation? Well, condensation is not just the loss of water. That's only part of a condensation. So there's more to a condensation. There's the dehydration part after the synthesis part. Do you remember that? So condensation and I'll reword it like the biology people, but I'll put them in the right order. Synthesis, dehydration, plus synthesis plus dehydration. They call it dehydration synthesis. The mechanism always involves the synthesis first. We'll see one very soon, near the second half of today's lecture. And a dehydration is just the dehydration. It doesn't have the synthesis at all. So there's no synthesis in a dehydration, like this one here. A molecule loses water. Definitions. You want 2 redone here? 2 redo with definitions? Condensation. Bring 2 molecules together to make a bigger molecule or larger molecule while also losing a small molecule. Notice I didn't say water. It's very often water. You can write often water. In biochemistry, it's quite common that it's a phosphate group. And dehydration a molecule loses water. It's that simple, everybody. I don't know what's going on here. Trying to write and it's shrinking, expanding, doing a whole bunch of stuff. There you go. I don't know. I think you've had enough too.